Okay, so here we are, first video for Unit 6, Simple Harmonic Motion in AP Physics 1. Here we're going to look at what are these restoring forces. So what causes these oscillators to return back to equilibrium? Because that's what these forces want to do. Okay, so restoring force is a force that attempts to bring an object back to its equilibrium position. And what's going to happen is it's directly proportional to some sort of displacement from equilibrium. Now, again, sometimes the examples or the wording will sound like it's a mass on a spring. Sometimes it'll be it'll sound like it's from a pendulum. So this kind of definition of directly proportional to the displacement from equilibrium, that is definitely about the mass on a spring. So, but also note, the restoring force will, will act in the opposite direction because at the extreme, so when the mass spring system is fully extended out or when the pendulum is pulled back, right, or in its swing, right, it wants to stop the object, right? That's why it's in the opposite direction of the displacement, so that it can stop it and so that it can return it back to, it can restore it back to equilibrium, because it's the natural state for objects to be, not moving, okay? Now, the two examples for restoring forces here in this unit are going to be Hooke's law and the force of gravity on with a pendulum, okay? So remember, Hooke's law is F equals kx, right? So spring constant times x. But when we look at it, if we're trying to accelerate the object, we know that F is m times a. If I kind of follow along my path here, that gives me an acceleration of kx over m. So this is the force, or you can put in a minus sign right here, because this is the acceleration, and negative kx is the force that is trying to stop that spring, right? So it's going to come all the way out here. The acceleration, because the object is moving this way, the acceleration will move in the opposite direction, which is where the force is, because it wants to go back to the equilibrium position, okay? Now, with the pendulum, it's a little bit more involved, but if we look at if we draw a free body diagram, at the extreme, we would have the tension and then the weight down, right? Tension kind of at an angle. Right, we have the angle up here, and so if you go through the process of draw, sum, solve, you end up working up, and I'll just kind of write this in. You got Ty equals mg, so this will be T cosine theta equals mg, right? Which makes T equal to mg cosine theta, mg over cosine theta, and then we go to the other side. We have Tx equals ma. This a is our acceleration that is going to restore. Okay, and so you would have T sine theta equals ma. We'll do it in a different color here, but I know T is mg cosine theta times sine theta equals ma, but you can see m's would cancel out. If I kind of go along, sine over cosine is tangent, and so I know the acceleration is going to be g tan theta, right? So that would be the acceleration, right? That's going to cause this to come to a stop. And so basically there's going to be no example problem here, because these are the restoring forces and the restoring accelerations that you may have to derive on the test, okay? So in the next video, we're going to look at exactly what simple harmonic motion is, right? And then we're going to dive into a little bit of these problems, right? So some of the example problems.